All right, we've got a real head scratcher for you today, one that comes straight from the world of programming but has a lesson for all of us. It's a story about how sometimes the solution that looks slower on paper is actually, believe it or not, way, way faster in the real world. Let's get into it.
Okay, so let's start with a classic problem. Imagine you have a list of numbers, and it's all nicely sorted from smallest to biggest. Your job is to find one specific number in that list. Now, if you've ever taken a computer science class, you probably know there's a right answer here. It seems pretty obvious, doesn't it?
You've basically got two ways to go about it. First, there's the brute force way, linear search. You just start at the beginning and check every single item until you find what you're looking for. Then there's the smart, elegant way, binary search. You jump right to the middle of the list. If your number is bigger, you ignore the entire first half. If it's smaller, you ignore the second half. You keep doing that, cutting your problem in half each time. On paper, it's not even a fair fight. Binary search should be 1,000,000 times faster.
But then reality comes knocking. Get this. A developer working on some high-performance code found that for smaller lists, we're talking anything under about 128 items, the slow, brute force linear search actually demolishes the fast, clever binary search. And this isn't just some weird fluke. It's a known optimization that's used in professional, real-world code. And that right there is our mystery. How on earth is that possible? I mean, everything we're taught, all the theory, says that O log n is always better than O of n. That's like rule number one of algorithms. Well, it turns out the answer isn't in the theoretical rulebook, it's in the machine itself. So to really get to the bottom of this, we first have to understand the language we use to even talk about this stuff. And that means we need a quick look at something called big O notation. Now, the most important thing to get about big O is that it's not a stopwatch. It doesn't tell you how fast something is in seconds. Instead, it's more like a crystal ball. It tells you how an algorithm's runtime is going to grow as you throw more and more data at it, all the way up to a nearly infinite amount. The keyword here is scaling, not speed. And when you look at that scaling on a chart, the difference is just insane. The line for linear search is a steady climb. More data, more time. But the line for binary search is almost totally flat. You can add millions, billions of items, and the time it takes barely even budges. And that massive difference in scaling is why everyone will tell you that binary search is superior.
So yeah, here's the textbook version. Linear search is O of n. Binary search is O of log n. Looking at this, it seems like an open and shut case. Case closed, right? Well, not so fast. Here's the catch, and it's a huge one. Because big O is so focused on that infinite scale future, it deliberately ignores all the messy little details of the real world, what we call constant factors. We're talking about things like how a modern CPU actually thinks and how it grabs data from memory. And in our paradox, those messy little details change the entire game.
Okay, so let's pop the hood. It's time to stop talking about abstract theory and start talking about the nuts and bolts of how a modern computer really gets things done.
And here's the absolute key. Performance isn't just about counting the number of steps in an algorithm. It's about how nicely those steps play with all the incredible, clever tricks that are built into a modern CPU to make it go fast. And as it turns out, the simple, dumb, linear search is the CPU's best friend.
The first of these tricks is called branch prediction. Think of your CPU as an incredibly fast assembly line. When it comes to a fork in the road, like an if statement in your code, it can't afford to just stop and wait for the answer, so it makes a guess. It gambles on which path the code will take and starts working on it ahead of time. If it guesses right, great, you get a massive speed boost. But if it guesses wrong, it has to slam on the brakes, throw out all that work, and start over, and that is very, very slow. Now, this is where linear search has a secret superpower. The question it asks over and over again is this the number I'm looking for? And the answer is almost always no, 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 until you find it. The CPU's branch predictor sees this incredibly simple pattern and just keeps guessing no, and it's right almost every single time. That assembly line just keeps humming along. But binary search? It's a complete nightmare for the predictor. Every single check, is my number higher or lower, is a total 50-50 coin flip. The CPU has no idea what's coming next, so it guesses wrong about half the time, leading to those super costly pipeline flushes again and again.
Okay, hardware trick number 2, memory prefetching. See, your CPU is lightning fast, but your main computer memory, your RAM, is, by comparison, really slow. Going all the way out to RAM is a huge waste of time. So to speed things up, when the CPU asks for one piece of data, it also grabs the entire block of data sitting right next to it, assuming I probably need that stuff next. That little block is called a cache.
And once again, linear search is perfectly designed for this. It moves through memory in a straight line, one item right after the other. The prefetcher can see this coming from a mile away and has the next chunk of data already loaded and waiting in the CPU's super-fast cache before it's even asked for. But binary search? It's chaos. It jumps from the middle of the list to the first quarter to the third quarter. It's all over the place. The prefetcher can't predict this at all, so the CPU ends up sitting around waiting for those slow trips out to main memory.
And it doesn't even stop there. The sheer simplicity of the linear search loop lets the CPU pull off even more magic. It can use special instructions to check like 4 or 8 items at the exact same time. It can process different parts of the loop in parallel, and honestly, the underlying code is just way simpler for the CPU to handle. When you add all these little hardware advantages up, for small datasets, it's an absolute landslide victory for linear search. So now that we've kind of cracked the paradox, let's just zoom out for a second and remind ourselves what we even mean when we use the word algorithm.
At its absolute core, an algorithm is just a recipe. That's it. It's a finite list of well-defined steps you follow to get from a starting point to an end goal. It doesn't have to be complicated or mathematical. It just has to be a clear, complete set of instructions. And a good algorithm, just like a good recipe, has to follow a few rules. You need to know exactly what you're starting with. You need a full series of steps. You need to know exactly when you're done, and every single step needs to be crystal clear, with no room for confusion. And you know, this isn't just about computers. Converting Fahrenheit to Celsius is a perfect everyday algorithm. You start with a number. You follow 5 simple, unmistakable steps in the right order, and you get your answer. That's an algorithm in action. Which brings us all the way back to the heart of our puzzle. And this quote from the original discussion just hits the nail on the head. Big O notation is a brilliant tool for talking about theoretical efficiency at massive scale. It is not a tool for measuring real-world performance. So you see, both of these viewpoints are totally valid and super important. Theory, using Big O, tells you what's going to happen when you're dealing with millions or billions of items. But practice, the nitty-gritty of how the hardware works, tells you what's actually going to be fastest for the list of 100 items you deal with every day. And that, right there, is the big lesson. The best algorithm isn't some abstract theoretical idea. It's a practical choice that totally depends on your specific problem, your data size, and maybe most importantly, how well the steps of your algorithm line up with the strengths of the hardware that's actually running the code. You know, it's pretty wild. If theory and reality can be this different for a problem as simple and fundamental as searching a list, it really makes you wonder, doesn't it? What other basic assumptions do we have about performance and efficiency that might be completely wrong when the code actually hits the silicon? Definitely something to think about. Thanks for watching.